Hello everyone, my name is Satish Rasta. Today we'll be discussing analysis of DC systems. First, I would like to begin with the discussion of how short circuit currents are calculated using some approximations. We have used steady state approximations. For cables, the circuit inductance and the capacitance are not considered, and therefore the transients that occur during a short circuit because of the capacitance or the inductance are not modeled. The worst case short circuit currents are provided by the steady state, and thus the resistance component is taken into account when building the network for the system. DC motors contribute to bus faults, but loads do not. So entering the motor resistance in the dialogues is important for short circuit calculations. When we model rectifiers, we have to enter the fault information in the rectifier dialog. And lastly, when we're talking about DC values, these are average values and they are slightly different from what we typically refer to for AC systems, that is RMS values. Now let's talk about the various DC components. For DC sources, we have DC generators. We also have DC utility. Then we have photovoltaics or solar cells, then batteries, and then rectifiers. For loads, we model DC load and DC motors. DC motors, again, they contribute to the short circuit currents at a bus fault. Other components, we model DC cables, and for converters we model rectifiers that convert from AC to DC, and then inverters that convert from DC to AC. For DC protective devices, we have DC fuses and DC thermal magnetic breakers. This is just a quick representation of a machine model, a DC motor or a DC generator. We have the magnetic field and we have the rotor, where we have the armature conductors, and they're connected to the brushes and commutators, and they are connected to the rest of the system via the terminals. When modeling a DC generator, the voltage that we receive at the terminal of the generator is given by this equation: the induced voltage on the armature minus the voltage drop across the armature circuit. Similarly, the DC motor equation is given by terminal voltage is the sum of armature voltage on the rotor plus the voltage drop across the armature, which is a multiple of the current and the resistance. When we calculate DC motor short circuit contribution, the terminal voltage collapses on the motor terminals if you have a fault on the terminals of the motor. And so the equation that we saw earlier reduces to this form. And so we are dividing the voltage by the armature resistance to get the short circuit current. For armature resistance, the best information is obtained from the motor manufacturer. If you do not have data and you're looking at old motors with very little, nameplate information, you could probably use some estimates. And in the next few slides, we'll be seeing some sample data of DC motors at 230 volt. This is a graph that we compiled based on the data we collected for 230 volt DC motors, and the ohmic resistance values that includes just the armature resistance plus the resistance on the commutators are converted to percentage by dividing by the base impedance. And so we observe a trend out here. Based on the size of the motor, we have lower impedances. This may not be true at all occasions or all samples, but for a starting point, this is a good enough data. So when we enter the motor information for resistance, we have to enter it in physical ohms. And the way we can calculate that is, for example, in this case, if we have a 20 horsepower motor at 230 volts and with a rated full load amps of 83 amps, we could probably start off by estimating a 5% impedance based on the previous graph. So with 5% impedance, we use this equation. So 5 divided by 100 is the 5%, multiplied by the rated voltage, 230 volts, divided by the full load amps of the motor, and we get the ohms for the armature resistance. So this is what you need to enter for the DC motor that you're modeling. The battery model is also fairly similar. We have a constant source behind the internal resistance of the battery. So the best information can be obtained from the battery manufacturer, and so you can enter that R value in the dialog for the battery. If you do not have any resistance information, then you could probably use some estimates. So this is what we have, and for flooded lead acid batteries, we have an estimate of 10% to 15%. For gel, we have 12 to 16%, and for AGM, it's about 2%. And this is from the reference stated below in this link. Let's take a look at example battery resistance calculation. So what we have is a flooded lead acid battery rated at 250 volts. The amp hour rating is 200 with an estimated 8-hour discharge time. So what we do is we calculate the base amps. So the base amps is 200 divided by 8, which gives us 25 amps. And so we calculate the resistance by taking the voltage divided by the rated amps, then we multiply the per unit impedance. So in this case, a 10% impedance converts to 0.1 per unit, and we get a total of 1 ohm for this example. Next, let's talk about photovoltaics. Photovoltaics has a very nonlinear V-I characteristics. So this curve shows what it behaves like in terms of voltage and current on the terminals. There are 3 key points that we need to keep in mind in this V-I characteristics. If you go to the left vertical axis on this, at this point, this is what represents the short circuit current. So when you have a short circuit, your terminal voltage is going to be 0, and the short circuit current you will get is approximately 10% higher than the rated voltage. Our rated conditions are going to be at this location here, and the open circuit condition is given by this location at the bottom along the voltage axis. So this is approximately 1.1 times the rated voltage, or you could also say this is 10% higher than the rated voltage at open circuit. So whether it's power flow calculation or short circuit calculations, we use this V-I characteristics to provide a solution for the analysis. For rectifiers, we are using Kimball's equation to solve for power flow, but these are only for power flow. We do not use this for short circuit. The basic approximation we should always aim for when we are modeling the AC side connected to DC side with rectifiers is your voltage should be very close to about 1.35 times the AC side. For short circuits at the load side, we can get, for diode rectifiers, currents that are equivalent to AC side faults. And for IGBT types or thyristor types of rectifiers, it may be slightly different, so it's best to check with the manufacturer so that you can enter it in the rectifier dialog. When we do DC arc flash calculations, we have followed the NFPA 70E 2012 edition and Annex D8 method for low voltage arcs. The arc current is assumed to be half the bolted fault current, and the incident energy is given by this equation. Again, you can refer to the standard for details on this. And this was derived based on some theoretical assumption using the maximum power transfer theorem. And in this equation, we have this factor, which is going to be dependent on whether it's open air or enclosed boxes. So when you have arc in a box, it's going to be 3 times higher than in open air. In this EasyPower example, we have the AC system coupled with the DC system. Here we have the utility feeding an AC transformer and AC switchgear. Then a rectifier converts AC to DC and feeds to a DC bus. So I'm going to zoom into this section where the rectifier is located. First, we'll take a look at how the data has been entered in this rectifier dialog. I'm going to double click on this symbol. So I get my dialog for the rectifier. The DC rated voltage is typically whatever your expected bus voltage is going to be. And earlier during the slides, I had mentioned that approximately there's going to be a certain ratio between the AC side and the DC side. And so this relation is typically in the range of 1.35 times the AC RMS value for the voltage rating. This is the full load amp rating for the rectifier. Then you can specify whether it's the diode type, IGBT type, or thyristor type. The type of rectifier is important for power flow because the equations used using Embark's method require whether it's an IGBT or thyristor or diode type, because we need to put in the commutation angles and the expected L over R ratio in the equations. When it comes to short circuit, we are modeling the rectifier as internally 2 isolated system. We have load on the AC side and we have a source on the DC side. So whatever short circuit is available on the DC side needs to be entered in the dialog. Typically, if you have a diode rectifier, any short circuit current on the DC side is going to be equivalent or very close to the AC side fault currents. So you can do the calculations on the AC side and enter an equivalent DC value on this DC side by putting in the appropriate full load amps multiples in this field. The IGBT diode fault time is entered for limiting the duration of the fault. So this is going to be used in arc flash hazard analysis. So check up with the manufacturer on how long your fault is going to last on the DC side of the rectifier. Let's take a look at the DC circuit breaker dialog. You'll notice that this is very similar to the AC circuit breakers. So just enter the manufacturer type and style, and in the phase strip tab you can enter the frame description, the trip amps, and if it has an instantaneous adjustable setting, then enter that value here. Let's take a look at the DC bus dialog. It's important to specify the bus type because for arc flash calculations, there's going to be a difference of 3 times when it comes to comparing between open air arcs and arcs in enclosures. So the rest of the choices out here represent arc in a box. So this is the DC bus, and we have some loads being fed. If you take a look at the loads, we have a field to specify what your load is. You can choose either amps or kilowatt rating for the loads. And when we run power flow, we have 3 different types of model for the load. One is constant kilowatt. No matter what the voltage is at the terminal, is going to use the exact specified amount of kilowatts. For constant current, no matter what your terminal voltage is, it's going to use up the exact amount of amps that you specify. In the case of constant R, that's a constant impedance model. So as your voltage changes on the terminals because of the system conditions, your kilowatt or amp consumption is going to change because it's going to be based totally on the resistance of the load that we model. The scaling factor can be used for scaling down just in case your total connected load does not match with the actual consumed or measured values. Next, let's take a look at the cable information. So selecting a cable is fairly simple. Just choose the number of parallel conductors, choose the type just like you do for AC, choose the insulation, choose the size, and enter the length. So this resistance value that we have shown in this is for a one-way length, and internally when we perform calculations with its power flow or short circuit, since DC is pretty much like a 2-wire system, we do have to account for the return path. So return path resistance is included in internal analysis. Next, we'll take a look at the motors. So you can enter the rated kV for the motor and the rated horsepower. The RPM is just for information purpose. It's not going to be used for calculations like for AC systems using the ANSI C37 standard. And you need to specify the armature current. And the most important factor for short circuit calculations is this armature resistance R in ohms, and that is going to be used in the motor contribution to upstream fault. So you can build your DC systems just like you would build your AC systems. To pick any DC item, you can go to this DC equipment palette. So here are the various items that we have, and just drag and drop them, then enter the data, and you've got your one line built. So once your one line is completely built with all the data entered, you can then start your analysis. So first I'm going to go into short circuit analysis and fault a DC bus. I'm going to zoom in, and so to look at the short circuit currents, click on the momentary. Again, what we said earlier was we are doing just DC steady state short circuit calculations. We are not modeling any transients. So here we have, half cycle, 5 cycle, and 30 cycles, and they're meant for AC. So when you're looking at DC, it's adequate just to look at just momentary current, because they're going to be constant over time. For motors, we have excluded 30 cycle currents. So if you look at 30 cycle, you'll see that it's 0. And for arc flash, we assume that within a brief period of time, motor contribution is going to decay to, insignificant values. So you can see fault currents on the faulted bus. For other buses, what we're displaying is the voltage. So it's pretty much like how you would model in an AC system. So we've tried to make this seamless transition from AC to DC. If you want to create reports, just go to short circuit, options, and check the boxes for whichever report you want to see. And it is included, all the DC analysis is included with the same report as AC systems. Next, we'll take a look at arc flash hazard. Just click on the arc flash button here, and you'll get your arc flash results on the one line. If you want to create a report for arc flash hazard for DC systems as well, go to SC options, that's the short circuit option, then go to arc flash tab. Make sure that your checkbox is checked for arc flash spreadsheet. So if you have that, you can click on this arrange for arc flash button. This is new in the 9.6 version. Otherwise, you can go to window and choose arrange for arc flash from there in previous versions. And so when you fault a bus, at the bottom you should be seeing the arc flash hazard report. And a new item that we've added is AC/DC. So in the arc flash hazard report, you can see that this is a DC bus. To print arc flash labels, just select your report and choose the desired rows that you have in your report. Then click on label. So the program is generating the label preview right now. And this is what your label is going to look like. So that's the preview, and you can send it to a label printer or whatever printer you use for printing labels. So right now, let's say we wanted to look at DC bus. So this is the DC bus, and it's giving you the results for just the faulted buses. Okay, next thing we will do is take a look at power flow calculations. So I'm going to go into power flow and solve for power flow. So when we do the power flow solution, we look at all the DC loads, all the motors and the loads that we've modeled, and we calculate the DC side there. And based on whatever consumption there is. So let me switch. Right now it's reporting. Let's take a look at what it's reporting. So on the branches we're reporting megawatts and megavars. For DC, megavars don't come into account, so we're just looking at megawatts. So you have the choice of looking at kilowatts, or you can also show current in amps as a solution. So these are kilowatts. So what we do is across the rectifier, we take this value of kilowatts and we use Kimball's equation to translate that to what would be seen on the AC side. Next, we'll take a look at how we can utilize, DC trip devices in coordination. I'm going to select the main breaker and one of the feeder breakers on this DC bus. Then I go to coordination focus and plot a TCC. So these are the two breakers that I have. So you can see there's a little bit of overlap. In order to coordinate it, I would probably have to slide it slightly to the right for this main breaker. And you'll notice that there's an overlap at the bottom. For molded case circuit breakers, that is, typically going to be the case. There's going to be some degree of overlap there. So that is how you can carry out some of the analysis in EasyPower. We discussed power flow, short circuit, arc flash hazard, and coordination.